Okay, so pick some algebraic plane curve. In this particular example, I'm using a degree 6 curve governed by this equation up here, and this is also sometimes called a 4-petal rosacea curve. Okay, and now define a point O in the plane of this curve and draw a circle, the red circle with some radius that I'm controlling by this slider over here on the left, right? Now also plot the n intersections of this circle with the plane curve. Now, because this plane curve has degree 6 and the circle is a degree 2 curve, there should be 12 intersections in general, the product of the two degrees, Bezout's theorem. But in the particular case that I'm showing here, I can only see 8 intersections marked Q1 all the way through Q8. Okay. Now, one interesting remark is that the centroid, meaning the average of all the intersections of the circle with this generic plane curve, that centroid, which I'm marking here at C0, is independent of the radius of the circle. So I thought this was a pretty cool phenomenon, and you can replace this plane curve by any other plane curve. Now, in general, we should be able to see the 12 roots here. So there's 4 of them that are in the complex plane, they're complex. But somehow we're getting lucky here that those 4 missing ones are not affecting the stationarity. But in general, you would have to algebraically compute all 12 and make the statement that their sum, in this case I'm doing the average, right? It's the same thing, but that sum is independent of the radius of the circle. So if I move O, for example, I place O over here, I can place O anywhere, right? So if I place O over here, for example, and I do the same experiment, I get a different C0. Okay, now you can see here that if the radius becomes too large, you're going to start getting the fusion of Q1 and Q3, and at some point they're going to bifurcate toward that Q1 and Q3. They used to be over here, now they're complex. So now you need to somehow do the algebra, including the complex roots. In general, there are, as we said before, 2 times 6, 12 roots. And you need to make that argument involving all 12 roots, all 12 intersections, okay? So I thought this was a pretty cool result. So for example, I can go to any one of these petals, okay, and they are symmetric, okay? But wherever I place O, if I vary the radius of that circle, you're gonna get this stationarity of the vertex centroid of those n intersections. All right, that's all I have. See you on the next video.